from Houston watching us. I'm just going to take 30 seconds because I want to name of SPE, thank Total for the sponsorship. And in name of Total, thank SPE for the organization. I want to thank Rafaela for the organization from Total, Camila, João, who's going to do the introduction. He's our ATC manager for Total. Anderson, who did the whole event organization stuff. And Clarice, our staff from SPE that made this whole event possible. I'm going to call now João, who's going to make our introduction.
Thanks, Rodrigo. I would really like to be the Total HSE director, but in fact, I'm working in safety to SPE. But I'm studying French. Hi, Dr. Kaplan. We really thank you for your availability and interest on sharing such relevant content to our Brazilian safety community. We really appreciate your time as well as congratulate you putting efforts on this scope, a key scope to us in terms of safety. We'll just say some words in Portuguese what it is here through web about SPE, the importance of PRA to support preventing the recurrent accidents we have seen around the oil and gas sector. Yeah? Just a moment. Pessoal, apenas reforçando aos ainda não membros, a SPE, ela reúne mais de 140 mil membros em todos os continentes, vem trabalhando há mais de 50 anos para a disseminação do conhecimento técnico na área de petróleo. Nossos eventos são sempre de alto nível técnico, políticos, não comerciais e atendimento à nossa missão primária. Legal? A gente agradece a vocês aqui a presença em mais esse evento, para aqueles que já têm estado conosco em diferentes sessões técnicas. E aqueles que nos conhecem sabem que a gente prima por trabalhar a questão técnica, a disseminação do conhecimento e a nossa evolução como profissionais do setor de óleo e gás. Certo? Estou fazendo uma coisa que eu particularmente detesto aqui, lendo, mas senão eu vou ficar falando por muito tempo, que não é o objetivo. Hoje o foco está no Dr. Kaplan. Tá certo? Então, nós pedimos aos profissionais da área de segurança que estão presentes ou conectados via web para dedicarem especial atenção à apresentação do Dr. Kaplan. Acidentes continuam, infelizmente, correndo, apesar de todos os investimentos em sistemas de gestão e tecnologia. Tá certo? Mas, de qualquer maneira, a gente vê ao longo do tempo que eventos, muitas vezes catastróficos, danos ao homem, ao ativo, industrial, ao meio ambiente, continuam ocorrendo. Então, algo tem que ser feito. Normalmente, quando algo tem que ser feito em termos de engenharia, a gente está falando em muito estudo, em muita preparação prévia, e é o que a gente está fazendo aqui, hoje, nesse momento. Então, todos os estudos que nos levam ao desenvolvimento de melhores mapeamentos de risco, análises, avaliações de risco, mais robustas, devem ser considerados, obrigatoriamente considerados, e é o que a gente está fazendo a partir desse evento. Então, convidamos também a todos vocês presentes aqui no GAE e via web a nos acompanharem no seminário de segurança operacional offshore, que está sendo desenvolvido nos dias 26 e 27 desse mês, ou seja, daqui a 15 dias, na Firjan, aqui no centro do Rio de Janeiro, e já contempla uma grade muito boa sobre segurança operacional em offshore, com a presença das autoridades e alguns personagens notórios saber na área de segurança, e ao Congresso Nacional da Associação Brasileira de Risco, também na Firjan, em outubro e novembro. São profissionais de uma entidade ligada a nós e que desenvolvem estudos de risco e confiabilidade em alto nível também, merecem toda nossa atenção ao trabalho que vem sendo desenvolvido lá. So our special thanks to Total for support in one more initiative, and Anderson, who made all of this happening. After Dr. Kaplan's kind lecture, Anderson will address our questions to Mr. Kaplan to ensure making these concepts clear, despite knowing that there is much more ahead to learn about probabilistic risk assessment. Dr. Kaplan, please be welcome on board and let us work.
Well, is it time for me to begin my presentation?
That's it. We're ready for the event.
Excellent. Well, thank you very much for your kind invitation to speak to the Society of Petroleum Engineers, the young professionals group in Brazil. It's quite an honor. Unfortunately, I have this internet connection, so I'm hopeful that you'll be able to hear me clearly and see my presentation charts. So I certainly apologize if there are any disturbances in clear communication. And also I apologize that I do not speak Portuguese, so I am going to be forced to speak English. Please let me know if at this moment you can see my presentation chart. Is this, can you see the chart?
No, not just yet.
Please say that. Yes?
No, not just yet. No, David.
Oh, okay. It's probably my fault for not figuring out how to share the screen. Let me try that one more time. Excuse me. And I believe I've done my magic, so we'll try it one more time.
We can see you now.
Again, thank you for the chance to speak with you. There are actually 4 questions that I'd like to address over the next 40 minutes or so, and then be open to answering any questions you may have. The 4 questions are really, why does NASA have any experience that the oil and gas industry should be looking at? The second question I want to discuss is, what is that technique that NASA has successfully used in assessing risks for the space shuttle and the International Space Station, and frankly, many of the large projects we undertake. The third question I briefly want to discuss is, what is the relationship between NASA and the US regulator, BSEE, the Bureau of Safety and Environmental Enforcement? And finally, I'd like to describe to you some of the activities that NASA has done with members of your community, in particular Anadarko Petroleum and Shell. So the first question is one I'd like to just address. And on initial thought, it's not really obvious that the International Space Station has much in common with deep water offshore operations. But perhaps I can sway you to think differently. The initial module that began the assembly of the space station was launched in November of 1998. Nearly 2 years later, the first crew, an American and a Russian, docked to the station. That was on November 2nd in the year 2000. So for more than 16 years, we have had continuous human occupancy of the International Space Station. And I point that out to let you know space station is a mature facility. Like many deep water offshore rigs, it's been around for a while, and it's not pristine and it's not new, and we have to wrestle every day with issues of reliability and maintenance. 222 individuals from 18 countries have visited the International Space Station. Marcos was a visitor in March of 2006. The 5 major partners of the space station are Russia, the European Space Agency, Japan, Canada, and the United States. So you can understand that the ISS, the acronym for the International Space Station, must deal with different cultures. Cultures from international government agencies, cultures from prime contractors, cultures from many subcontractors. Well, perhaps the most obvious statement of all is that the International Space Station is an extremely complex engineering structure. If you were to look at the habitable volume of the space station, it is larger than a 6-bedroom house. but that's a little misleading because in your houses, you can't equally use the ceilings, all four walls, and the floors. It's pretty clear that maintenance is a critical component for long-term reliability. Repair is something that is absolutely necessary, oftentimes done in very hostile environments. So critical components fail, and you must address them in order to keep your long-term operations flowing. You know, it's difficult to get to the space station, so we require very careful planning and preparation for the transport of our crews and all of the supplies. This coordination is incredibly essential to the success of the station. The space station travels at 28,000 kilometers per hour. It orbits the Earth once every 93 minutes. You get a sense that it's pretty isolated. Decide to jump on a quick ship and dock with it anytime you wish. So let me summarize kind of quickly why I think the International Space Station is a reasonable analog for deep water, offshore oil and gas operations. Both exist in a hostile environment. Both are extremely complex engineering structures. Both can be very mature facilities, easily 15 years or more. Both the offshore rig and the International Space Station operate at a remote location where the movement of the crew and supplies must be carefully choreographed. On both vehicles, human reliability plays a critical role to success. I think both industries, oil and gas and aerospace, have a deep commitment to both personal safety and process safety. Both have onboard crews, and those crews are supported by onshore support experts. NASA, we call it the Mission Control Center. And really, if there's one single point, it's failure is simply not an option. If we have a bad day on the space station, or you have a bad day on an oil rig, we're on the front pages of every newspaper around the globe. No one wants to be in that situation for the wrong reason. So I hope I've made the point that what NASA has experienced may have some relevance to your industry. I now want to shift gears and talk a little bit about probabilistic risk assessment. So before I dive into that, let's kind of step back for a moment. If NASA had 100,000 space stations, each having operated for 40 years and having a particular catastrophic failure rate of 500 of them, then we could do standard statistical analysis, and we could estimate the probability of a failure based on the large quantity of data we have. But we only have one space station. It's extremely unique, and really 16 years is a minimal amount of experience, and thankfully we have had no catastrophic failures. So the question becomes, how do you assess risk when there is no statistical data? And that's where NASA has focused on this technique called Probabilistic Risk Assessment, or PRA. And so I will make an assertion that perhaps PRA could be of value to the offshore oil and gas industry. Let me make one other distinction for risk management. There are qualitative approaches for risk management, and those are typically based on experience and expertise. At NASA, we certainly use qualitative risk assessment techniques. We call them failure modes and effects analyses, hazard assessments, fault trees. The oil and gas industry is outstanding in your use of qualitative risk assessments. I've seen bow tie charts, barrier analyses, process safety methods, things which are extremely well done, well thought through, and I have the highest regard for your industry's use of qualitative techniques. But NASA has found it's very difficult to use qualitative techniques to identify and rank low probability, high consequence events, particularly in complex scenarios like a space station. So we have added to our qualitative assessments a quantitative approach to look at empirical data and be able to assign numeric values with error bars to the risks, and that's the basis of the PRA. When you begin a PRA, the very first thing you need to do is define what end state you are looking to prevent. So a PRA analysis is a long, complex activity. It's not quick. It's not something that you would do for a simple facility. It is something that only has value if the potential negative consequence has a huge cost to it, either in terms of lives or property or damage to the environment. Do not begin a PRA lightly. But if you are going to begin a PRA, define the boundaries of the analysis. And in the jargon of PRA, we ask, what is the end state which needs to be mitigated? For the Space Shuttle program, the end state was the loss of the vehicle and the loss of the crew. That was what we wanted to prevent. For deep water offshore operations, the end state could be to eliminate significant threats to the crew from such events as a blowout, or maybe failure to contain large quantities of hydrocarbon. Now, I'm about to show a sequence of charts about PRA, and I absolutely realize you cannot read them. They have small font. In fact, my intent is not to have you read them and delve into the small detail, but rather to appreciate the flow. It would take probably 4 hours to give an adequate overview of the flow being a PRA, and certainly take about 3 days to explain all the technical details. We are not going to go into that level. But what I want to make as a point from this particular chart is that the PRA is a systematic way to connect the design, the logic, the operations, the human interaction, and external influences, things such as weather and hurricanes, for example, and to systematically connect all aspects of a large complex structure and the operations that go on in that structure in order to detect the dependencies that could lead to the negative end state we want to prevent. Now, I'll tell you that two areas where the PRA is particularly useful is in identifying where human reliability or human failures can lead to the negative consequence, and also where common cause, where a particular piece of hardware, say a pump, which might be located in 5 or 6 different areas unrelated, where one fails, the others become suspect because they were from the same lot and the same vendor. And in fact, when I do get to some of my examples later of work we've done with Anna Darko, I'm going to come back and talk more about human reliability. Again, I'm kind of foreshadowing a key finding, but we were very surprised that the humans have such an important role in those low probability, high consequence events that the PRA looked at. But again, that will be talked about a little bit more. This next chart, again, impossible to read, is a master logic diagram which is created for all aspects of the complex machine and processes we're examining. We use the qualitative techniques to identify the initial events. We rely on the expertise and the experience of the industry to look at what initial events could potentially lead to the end state of concern. So each event may, with potential negative failures considered, lead to that end state of consequence. We then take the initial events and they're mapped through what would be their normal routine process that would be used to mitigate them. I know you can't read the sequence of pivotal events on the top row, but if you began at the left and you did have an unexpected overpressure zone while drilling, then the normal way to handle that are those pivotal events listed along the top. We look at all possibilities of success, and each creates a new scenario that accounts for contingencies as well as those failures. You may notice that this event tree is time sequenced. Time moves from the left towards the right. So the pivotal events are listed along the top. And again, each pivotal event can either have success or failure. The scenario ends when a stable state is reached. So in this example event tree, the stable states, which again would be impossible for you to read on the far right, are either that the well is shut in, or there is a limited release of hydrocarbon, or that a new tree is initiated to manage the accident. So perhaps if someone's in the front row and squinting, they see accident management as an end, as a stable state. That would not technically be true. It's actually a pointer to another event tree. If we did this kind of event tree for all the possible initial conditions, it absolutely requires software programs to keep track of what would be tens of thousands to hundreds of thousands or even more pathways through a large complex facility such as the International Space Station or possibly a offshore deep water rig. The PRA is useful in displaying the probabilities of one or more of these stable states. So this is a notional example where different stable states distinguish the method that was used to kill the well. And when you're doing things quantitatively, you always have to be aware of how accurately you know those numbers. So there is always going to be uncertainty bars produced to show a range of expected values. And if one were to look at this particular chart, and you already assumed that we were going down the path where we needed to kill the well, the most probable way of doing that would be to experience a limited release, followed by the well being killed by an ROV, followed by the well being killed by well capping it. And the lowest probability would be to have to drill a relief well. So sometimes it's not intuitively obvious which way the probabilities go, but this is one situation where one can then sit down and have a discussion about the likelihood of needing to drill a relief well versus needing to have your ROV ready to perform when needed. Another power of the PRA is to show rankings, and many different ways rankings can be displayed. This particular example shows rankings of the initial event contributions to an oil spill. And so for this notional example, clearly a swab effect is more likely than, say, incorrect mud density to induce a kick. System hardware can also be ranked, and sensitivity studies within the PRA can be performed to estimate how changes in risks would occur if a component or a human action were to fail or to be successful. So we're able to look at different maintenance procedures, different work instructions, different levels of training, or different types of components, and see how sensitive the overall risk would be to those changes. And looking at results in these different ways provides a much clearer picture of the importance of events that are necessary to mitigate that negative consequence. So that surely was a very brief, high-level overview of PRA, but I would ask you to keep in mind the two previous charts. I believe that they would be very useful in effective communication between an operator and a regulator. So let me talk a little bit about NASA and BSEE. When it comes to drilling in deeper waters, drilling at higher temperatures, higher pressures, using new technologies, or using old technologies in new ways, BSEE, and I honestly believe ANP, really wants the operator to effectively and accurately communicate the risks of operations. All of my discussions with BSEE have centered around not trying to impose dictatorial rules on the operator, but really trying to understand what the real risks are. The key question is, how can the regulator be convinced that risks are understood and appropriately mitigated? And anyone who says they demand that the risks be zero is living in a fantasy world. If you want to have zero risk, don't drill. If you want to have zero risk in NASA, never launch. So given that we're committed to launching at NASA or drilling in Brazil, one needs to effectively communicate where risks are being taken. In particular, NASA and BSEE, both agencies of the US federal government, signed an agreement in March of 2016. We agreed for 5 years that NASA would work with BSEE to share our insights into probabilistic risk assessment techniques and provide our insights to BSEE. So with its qualitative risk methods, as well as PRA, NASA has demonstrated excellence in leading the international partners on the space station and the many contractors in assessing and mitigating the risks of operating the space station. We were brought to the attention of BSEE because of this, and I would say that BSEE is curious if PRA might be a tool for better communication with the operators about risk. Now, I am absolutely certain BSEE has made no commitment to imposing PRA. There's been no discussion about it becoming some kind of a new burden in the US. But where we are now is that they're interested, they're curious, and they're looking at what PRA could potentially bring to the table. NASA was asked to conduct 4 activities for BSEE. We have taken the guide that we use at NASA of how you prepare a PRA. So if tomorrow you told me NASA has to build an outpost on Mars, tell us what the risks are, we would go to our PRA procedures guide for NASA and begin going through it systematically to assess the risks of that new project. Well, BSEE asked us to take our NASA guide and modify it for applicability to offshore applications. So we prepared the PRA procedures guide. It's intended to assist in the development of a PRA for offshore drilling facilities. Draft version number 1 was to the BSEE website in February of this year. We're working on draft version number 2, which provides more augmented appendices with more relevant data for oil and gas. We expect to have version 2 posted near the end of this calendar year. And you will see the address at BSEE to download that approximately 300-page, very detailed guide, should you feel so motivated. The second area that NASA has been looking at is initial modeling of a deep water ship drilling an exploratory high pressure, high temperature well. The PRA end state, that negative effect we don't want to see, is called large release of hydrocarbons. And NASA is currently refining the logic and identifying our additional data needs for that deep water drilling PRA. Now, I'm betting that many people sitting in that room, even though I can't see you, are really saying, all well and good, but without good data, how can you possibly have an effective assessment? And that is an excellent question. You see, within my industry, the aerospace industry, NASA has pretty much complete control over all of the information from our international partners and our contractors. We know about all of the close calls, all of the near misses, all of the changes in procedures. We don't operate the way you do in a competitive industry where proprietary information can provide advantage for one company over another. So we are working with BSEE to address several questions about industry data assessments. So we're asking the question, what data is currently publicly available? What's the maturity and usefulness of that reliability data? What data is missing? Either because no one's ever asked for it or because it's considered proprietary and companies don't want to share it. What needs to be done to fill gaps in reliability data? And what would be a plan for somehow including or creating an industry database available to all, and perhaps doing it in a way that the regulator doesn't have insights into some of those close calls or near misses? I mean, we want the data. We don't want to punish anyone or have a regulator use that data in a way that might shut down the flow of good information about reliability. Oh, and the fourth area you'll see on this chart, subsea production hardware PRA, is something that we simply haven't begun yet. So I come to now the fourth and final question that I want to pose, and really that is, what's NASA presently doing with members of your industry about PRA? Let me first talk about an agreement that NASA began with Anadarko Petroleum in October of 2015. And this particular agreement is called a Space Act Agreement. It's a legal mechanism for NASA to partner with industry to perform an activity jointly. So in this case, NASA understands how to set up and model PRAs, but we had no knowledge at all about blowout preventers, particularly a 20,000 PSI blowout preventer, which was being considered for some newer activities in the Gulf of Mexico by Anadarko. So between October 2015 and January of 2017, we worked with experts from Anadarko to complete a PRA of this one component. Now understand, ultimately, we all want to have an overarching PRA of deep water drilling activities. But you have to begin somewhere. And so we selected, with Anadarko's interest, a 20K BOP and modeled a generic version because no such device has ever been built. We determined the end state would be loss of containment. So again, the probabilities that result would all be related to the probability of loss of containment of the hydrocarbons. And what were the initiators that we considered? Well, one is that a well kick has occurred, and two, that an unplanned disconnect sequence is required. Now, because we were only looking at the performance of the BOP, we did not develop probabilities for how often would a well kick occur or how often would an unplanned disconnect be required. So ultimately, when we have at some point in the future an entire PRA, both of those initial events would have their own probabilities. But for the purpose of this PRA, we assumed that each would occur. And we had several key findings. And some of them were surprising to Anadarko. When we looked at the assumption that a well kick has occurred, we were all surprised how human error so dominated the probabilities that human error completely dominates over failure of equipment. Now, we all thought that human error would be an important factor, but it was surprising how strong it was. When we looked at unplanned disconnect sequence, human error was significant, but it was not overwhelming. Failures of the blind shear ram and shuttle valves were also seen to be important contributors. And I would say that Anadarko took the results of the study we did and have used them in communication, I believe, with 3 potential vendors who might build a BOP for them. And they're engaging in questions about what if, and this probability if that happens, with insights that they wouldn't have otherwise had. Anadarko was so pleased with what they were seeing from the BOP that they entered into another agreement, another Space Act agreement with NASA. This one began in June of 2016 and only concluded this week, July of 2017. And this second PRA for them had to do with dynamic positioning systems on a Class 3 drilling vessel. Well, what was the end state? The end state would be a loss of location. That's what you want to prevent. What were the potential initiators? One was drift off, where you've lost GPS signal and the vessel wanders into what they call the red zone, which you want to avoid being in. That would be one initiator. The second initiator was drive off. That's where the vessel is erroneously commanded to move, and the momentum that gets created is such that you cannot stop the vessel before it's wandered off station irreversibly. The third initiator is push off. That would be, for example, where a weather event occurs that exceeds the station caping capabilities. That's the surprise hurricane in the Gulf of Mexico that you were not prepared for and blows you off station. And so as we completed this study, as I said, just this very week, some of the key findings that I can share is that, once again, human error was important. In fact, human error comprised 81% of the overall risk. So what Anadarko is looking to do is focus on improving things like human factors, vessel-specific training, ergonomics, tools, and other factors that they believe could help to reduce that human's likelihood of failure. Now, at first glance, you might think that the generators and the thrusters would be important, and they are, but they only contribute about 10% to the overall risk. And that was a value we found to be a little lower than we might have expected. But upon review of the PRA, we see that a vessel's ability to operate in a degraded state during normal operations reduces the likelihood of generators and thrusters contributing to failure. The levels of redundancy within those generators and thruster subsystems and the independence of redundancy groups all reduce the risk. And also the ability to conduct repairs during normal operations turned out to be an important factor in reducing the hardware components of a DPS system. We have already signed our next agreement with Anadarko. I think you can see we conducted a PRA on the blowout preventer. That was an isolated system, and the dynamic positioning DPS system, again, isolated. And now what we want to do is tie them together, and we want to add other components to the PRA model. And so you'll see the kinds of things that we've agreed to do in the next iteration of our model. And As I mentioned, we just signed this agreement with Anadarko in late June, and we'll begin kicking off the activities to expand the BOP, the Dynamic Positioning System PRA models, really in just another week. I identified that we are doing some work with Shell. In fact, we just had our kickoff meeting with Shell last Thursday. And so I really don't have any results to present, but I'll share with you that where Shell was concerned, it has to do with the new well control rule that BSEE has put in place that will require offshore Gulf of Mexico operations to need additional hydraulic fluids and therefore additional accumulator volumes within 5 years. And Shell has some opinions about that rule and how much it reduces risks. And NASA is acting as a neutral third party. We take neither Shell's position nor BSEE's position. We will set up the PRA, we will run the assessment, and we will report out what the risk results are. So that really completes my prepared remarks. I'll be more than happy to take some questions. Let me just figure out how to turn the screen back over to you all. Let's see. Anderson, can you see me?
I think we have you. We're not seeing you
Okay.
yet.
All right, let me,
We got you.
you got me? I'm okay?
You're
Great.
good. So, well, first of all, I think I can say all of us here in the SPE Brazil section that we were very excited about this event, and it wasn't for little reason. It was a very great presentation by Dr. Kaplan here, and I want to thank you for the time.
Obrigado.
And I think now we're open for questions. I'm sure we're going to have many. So, before João is going to ask you the very first one.
Thanks again for your words. But this question, when considering all data created from the design phase up to the steps ahead management of changes, for example, in the future of the life cycle, maybe when engaging in human factors, for example, we create a huge amount of data. What do you think about engaging this data in powerful computation like IBM Watson, cognitive computation to support us on using PRA?
You know, I must apologize. During the middle of your presentation, the audio dropped out. So I'm having a difficult time hearing you. I hope you can hear me better. But could you repeat the heart of the question, please?
Yeah. Engage cognitive computation on processing all of these data from design phase up to management of changes, up to human factors, using something like IBM Watson system.
Well, I applaud all of the reliance on good data. That's essential to making informed, risk-based decisions. Where we don't see a complete opening of data has to do with reliability of hardware and reliability of human performance. These are areas where we would like to see some kind of a central database available to the entire community be created where Total, Petrobras, Shell, and Anadarko can all, with anonymity, enter their reliability information so that people who are preparing PRAs can use the most relevant data available.
Yeah, thanks. I in fact have a question of myself. I saw that you guys are working on a subsea guide, PRA guide. As a subsea engineer, that I thought that was quite interesting. One point that I actually raised in the conversation prior to this event with you was that one of the assessments, key issue on doing these types of subsea hardware assessment is when dealing with very low frequency events with high impact, such as, especially when dealing with geological timescale. And what I would think NASA to be dealing with the same sort of level of difficulty, especially when you start talking about setting a Mars base and going somewhere where you have very little or no data at all. How do you actually manage to deal with those kinds of combined low frequency and high impact events?
Yes, an excellent question. Let me give you, I think there were two questions in there, so I'll try and respond. First, to the question about the subsea production hardware. Anderson, I know you've said this, but risk is always a combination of two things. It's the amount of time you're exposed to a potential event and the significant consequence of that event. When doing deep water drilling, that's a very high time where you could have a spill and you have to be aware of it, but it's a relatively short period that you're exposed to that risk. Whereas subsea hardware production can go on for 15 years. And so there, the duration of time is long, even though the likelihood of a failure is small. And so we found that with the International Space Station, it's really the long period in orbit after assembly was complete that is a higher risk than those times when we were flying up the components to assemble it. So it's very important that we eventually do a PRA for the hardware on the subsea that's being asked to operate for 10, 15, 20 years and understand where the risks are for that set of hardware. Your second question points really to when you're doing something new and unique. Your example of setting up a base on Mars. Of course, you don't have relevant data in the environment of concern when you're doing something new. And the same is true when you're drilling deeper waters, higher pressure, higher temperatures. You have analogs. If you're building, for example, a blowout preventer capable of holding 20,000 PSI, that's new. But you built 10,000 PSI and 15,000 PSI blowout preventers in the past, so you have somewhere to begin. For a human base on Mars, we have the robotic vehicles, the Curiosity rover exploring the landscape and helping us to narrow the band somewhat of what we might encounter when we go to this new environment. But we will never have 100% complete accurate understanding of Mars until well after we've been there. So what you do is you create the PRA with the full logic, the master logic diagram, and when you go to create the event trees, you use the best reliability data you can. You base that on your past experience. And then you update your models ongoingly as you have experience. the technical name for the technique is Bayesian Updating, or the use of Bayes' theorem. It basically says that if you're doing something new you've never done before, you begin with your best guess, but then you ongoingly inform that guess based on the actual data you experience. And in this way, even though you've never had a failure of a space station, you can still understand whether adding the module here or there increases or decreases the relative risk. So again, if you're doing some kind of operation that's totally new, you still have a basis to begin with. And then the key is not to create the PRA one time, put it on a shelf, and allow it to collect dust. The PRA becomes a living document, and every week or 2 weeks or month, you update it with your new data, the new information, and then you assess its value. And I'll just parenthetically say, since I was part of this, when we were flying these space shuttles, before each launch, the mission management team would get together and they would have the space shuttle PRA updated for all the changes, all the maintenance, all the new objectives that this upcoming mission would be asked to do. And the management team went through all of the risks in the PRA, and those risks could change based on whether you were servicing a Hubble Space Telescope or delivering a module to the space station or bringing up a new laboratory equipment. And you wouldn't launch the shuttle until you had assessed how the risks had been updated. And I would assert, if I was a project manager of an offshore drilling operations on a regular basis, I would want to have the PRA updated with the latest hardware, the latest crew training, the newest maintenance procedures, and see how all that has affected this facility. I'll stop there.
Thank you. I think that more than fully answers the question. So any questions from the audience? All at once, please.
Well, it's late, I understand.
We're a little ahead of you. Okay.
Yes.
Just one question. It's very interesting. You mentioned in cases where you don't have the previous experience. You're excellent, for example, in the case of Mars or any project that you do not have this previous experience in using Bayes. Think about the unthinkable and in the States, especially in situations where we do not have this previous experience or have very little. You have any special techniques in the process of generating those end states?
Well, to me, the end state is always what is that situation that will put you on the front page of all of the world's newspapers in a negative light. It's got to be something serious like a BP Macondo spill, for example. It's silly to do a PRA on the living quarters on the rig and if the toilets get backed up. Well, yeah, you could, but what a waste of effort to do something on a trivial matter where you already know how to handle it, or the consequences of a failure are not really critical. Has got to be that thing that kicks you in your gut or causes you to wake up at night in sweat.
And the steps leading to this step, for example, the PRA analysis of the steps that causes that lead to this end state, also in particular, or just assessment, brainstorming, or
Oh, it's a very complex process. You might have noticed that for the BOP, we spent more than a year's time. Now, I admit working with Anadarko was not the priority for NASA. So I want to be clear, NASA has been working with Anadarko and BSEE and Shell as we've had resources available. But even so, it took about a year to understand the true master logic flow of the BOP and to get it down into our software. The space shuttle PRA took about 3 years to fully complete. So it takes time to work through the entire flow. As you said, you begin with your qualitative assessments from your experts, your past experience, the what ifs as you all sit in the room and say, well, we never saw this, but what if this crane fell or something happened? That's where you begin. And you lay out the PRA, and then you go through it rigorously. At each decision point, you have a node. So at each point, a piece of hardware and a human action can occur. So for example, with a pump, you could command the pump to turn on, but it stays off. You could command it to turn off, but it stays on. You could command the pump on, but it only operates at half the efficiency. The human being could push the button to turn the pump on, but outside of the window when he or she is supposed to. So the human being can do the right step, but at the wrong time. So all of these are possible permutations. So when you look at each node in the PRA and you ask, did the human successfully do what they needed to do or not? Did the hardware function the way it was intended or not? You can see the trees start to branch way off. That's why no human brain can understand all of the thousands of pathways through the logic flow. That's where the software has to come in to look at several nodes that may have very low probabilities, each one, but when they're added together in this unexpected way, potentially leads to the end state you don't want to see happen. That's
Okay, thank you.
all right.
Any other questions?
Well, I just have one quick question. I'm looking in the second row. Do I see my friend Eduardo? Ah, okay.
Okay, Dr. Kaplan, I have a question for you related to the Bayes theory. You have mentioned that you use the Bayes theory for updating data. You don't have much information, but I would like to know if using Bayesian networks is included in your model or not, and if it's not, what do you think about the usefulness of using Bayesian networks for risk assessment?
We do use Bayesian networks in our assessment. It's part of the software program we use. It's included as we perform the PRA. It actually is a software that is produced by the Nuclear Regulatory Agency in the United States. It was first developed for nuclear power stations and updating their risks as hardware was changed out and maintenance done. And so that's the software that we use here at NASA, but it incorporates into it the whole.
Okay, thank you.
Thank you.
Well, any very last one? Like this? Well, Dr. Kaplan, I think with that we can close the event, and I would like to thank you once again. It was an absolutely amazing event and one of a kind, and hopefully we can conduct more of these events. And I'd like to thank SPE and for the organization, Total for the sponsorship, and I'd like to and all of the people involved, João for hosting for us, and Rodrigo as well, and all the ladies over there back helping us out with the streaming, and showing me up. I know it's late, I know it's after work and everyone wants to just be home. So thank you all for coming. And I'd like to invite you all so we can end our welcome coffee over there and take the time to do some networking, get together, talk a little bit about the subject, which I think can be very useful to a 5-minute conversation, may lead to projects and collaboration. So thank you all. Unfortunately, I cannot invite you, Dr. Kaplan, for the welcome coffee. Perhaps next time you come and visit Brazil, we can definitely discuss some more. Thank you once again.
It would be my pleasure. Thank you.
Bom, pessoal, muito obrigado.